Thanks, David. And thanks to the organizers for inviting me. So I have to maybe give a quick disclaimer. So the talk was initially planned to be a 30 minutes talk, and I got a free upgrade to 45 minutes. Therefore, the topic, the upgrade was not quite free, actually. It came with a request to talk a little bit more generally about interdiction, and initially just wanted to talk about minimum spanning tree interdiction. So the talk is like two parts now. I will mostly focus on general interdiction, and then focus a little bit on, talk a little bit about a specific interdiction problem, this minimum spanning tree interdiction problem. So let me start on a very high level. So interdiction was first it's mostly considered by practitioners, and I want to kind of show you a little bit that point of view on a few very quick examples. They're not as exciting as Lex's example, Lex's application, but I hope you get a little bit the idea of what interdiction means. So maybe the global question is sort of very soft. The global question is how sensitive a system is with respect to discrete changes to a system, to removal of some of its components. So the main goal is you want to learn how robust the system is, and also to identify its weakest spots, sometimes to protect things, and sometimes to attack an undesirable system or process. So this, especially the protection part became quite famous, or people got quite interested in that after 9/11, actually, to protect infrastructure from terrorist attacks. So one of the very earliest applications is drug interdiction. So this is within the context of the US war on drugs, where the US tried to figure out how to best invest the resources, the limited resources, to help South American countries to interdict the flow of precursor chemicals that are used to produce later drugs. And so they modeled this as some kind of a flow problem, so standard, essentially kind of a max flow problem, and tried to interdict that flow problem. So I will come back to what I precisely mean with interdicting flow in a second, give a formal definition. But so, as I said, I will start with a really soft introduction. So another typical application is to interdict undesirable processes like disease spreading. There's a lot of famous models. One of them is the so-called SIR model, where you have individuals being either susceptible, which means they're still healthy and didn't have the sickness so far, or they're infected, or once they recovered from the sickness, they're removed. They're in the green state. And there's some kind of course, specific rules how those dynamics work in that graph. And with an initial infected node, and there's a kind of a random process that determines how infection spreads. And at the end of the day, you will have, so the disease spreading will stop. You will have a certain number of individuals who got the disease and recovered, and others who didn't get it. And the goal would be to somehow minimize the size, the number of people who got the disease, the number of green individuals here. And so for example, through vaccination. And so vaccination, you can think of it as you could, in the easiest, kind of in the simplest model, that you could kind of take out some of those individuals. You could kind of remove them from the graph. And you want to remove them in a way such that the expected size of the disease spreading is as small as possible. So that's one other typical application of interdiction problems, still without even having formally defined what it means. Another one that's also became quite known is hospital infection control. It's from the 80s, where people are interested how to increase, for example, hygienic measures, or more generally, just block the dissemination of germs in the hospital. It's a typical problem we also have nowadays, of course. And they've also modeled that as some kind of flow problem, where they modeled how germs spread within a hospital to try to figure out where to best attack that spread of germs to inhibit the germ dissemination. So it's really just a picture. It's taken one-to-one from that paper up there. So as I said, it's a lot of work now done on protecting infrastructure against terrorist attacks. And so again, one thing I would like to highlight here is we typically assume that the attacks are like worst case. So it's a bit different to some other models in robust optimization. So here it's first the worst case attack, and then after the attack, we look at the resulting system and then optimize over the resulting system, or let a process run on the resulting system. So it's really a two-player game that has a clear order. There's first the attacker, and then let's call it the optimizer or operator of the system. So now let me go slowly to more concrete settings, and so it's a connectivity workshop. So let me talk about some form of connectivity interdiction, just to fix things a bit more concretely. So here's given an undirected graph and with capacities. And so let me, for any pair of vertices, I call So the connectivity between these two, or the bandwidth, is simply the max flow you can send between these two vertices with respect to the given capacities. And the bandwidth of the whole network, or the connectivity of the whole network, is, of course, the minimum over all pairs of the bandwidth between any pair. So it's, in other words, it's a global min cut, the value of a global min cut in that graph. Now I could ask the following question. So assume that you want to make sure that between any pairs of vertices that there is a bandwidth of at least 3. So it turns out in that graph, actually, we have even, so the min cut has size, I think it's 8, actually. So it's even 8. So now, simple question. So how many edges do you have to remove at least to make that drop below 3? So in other words, how many edges do you have to remove to create a cut, a global cut in that graph whose value is 2 or less? That would be a typical interdiction question. So here, just to give some example, so here the answer is 2. You can remove these 2 edges, this one here and that one here, and this creates a cut, this kind of center cut, between the 4 central vertices of value 2. Okay, so there's a solution, fine. So a few observations I'd like to make here is, so as you see, so you can think of it as the attacker essentially tries to attack a particular cut, because you want to create a cut of value as small as possible. So you can think of the attacker first choosing a cut to attack, and then removing edges that are crossing that cut. And of course, you will remove the edges of highest capacity first. So that's kind of obvious. You know what cut you want to attack. It's obvious how you attack the cut. As you see, the cut that you attack is, of course, it doesn't have to be a min cut in the original graph. There are smaller cuts in the graph than this one. For example, the one that is, so I think that this is the smallest cut, I think, of value 8. And there are also smaller cardinality cuts, or cuts with fewer edges, like the singleton cut 1 up there, right? It's a smaller cut. So it's not, so it's really different. The cut you attack is really not, it's not completely clear how it relates to those quantities. So I can, for those who want to think a little bit about something while I keep talking, so you could wonder, is this problem actually polynomial time solvable to find the minimum number of edges you have to remove to make the global min cut drop below a certain value? Or in other words, if I give you a certain number of edges you can remove, can you determine what is the best attack to get a global min cut of value as small as possible? So I'll give you the answer later in the talk, without giving you the algorithm, but I can give you some details how this can be done. Good. So now this brings me to, I now want to define things more formally. So interdiction problems, so I want to talk about network interdiction, so I talk about network optimization problems. So there's always like a nominal problem. So think of the nominal problem, for example, as being a Maxim SD Flow problem. And just to fix things here, let's assume it's a maximization problem. But of course, things will also be, you can define it as well for minimization problems. It's completely analogous, there's no difference. So you're given a network, you're given an optimization problem like Maxim SD Flow, and with mu of g, I just denote the optimal value of that nominal problem. Furthermore, you're given interdiction costs on the edges and the global interdiction budget, or removal or attack budget. And so what is the task? You want to find a subset of the edges. So we call this R, like removal set. So it should be a set that is, whose cost is within the budget. So C of R is at most the budget B. And you want that if you look at the nominal optimization problem on the graph you obtain by removing this set of edges, you want this to be as bad as possible. So in the case of a maximization problem, you want to minimize that. So on this example of Maxim SD flows, you want to minimize the value of a Maxim SD flow. And so clearly see it's an ordered problem. This first minimization, so you first remove stuff, and then you thanks Andras, and then you compute a Maxim SD flow. So special case it's nice to keep in mind, which essentially corresponds to what I've shown you beforehand with the connectivity interdiction, let's call it that way, is to have unit interdiction costs, so unit removal costs. There you simply want to remove a certain number of edges. It's a special case. So essentially, so you see that you can essentially define, for any nominal optimization problem, you can, on the graph, you can immediately kind of mechanically define a corresponding interdiction problem. So it's kind of a very general way of defining things. So of course, if there are any questions at any time, don't hesitate to interrupt me. So now I would like to start with some general techniques for attacking such interdiction problems. And as I said, I'll later go to a more specific one, to the minimum spanning tree interdiction. So first, as you've seen, those problems are like min-max problems. If the nominal problem is a maximization problem, it's a min-max problem. So one way to get to just a minimization problem is to dualize the nominal problem. So the nominal problem here was, for example, So let's look at a simple example. Let's assume that the nominal problem is a maximum cardinality bipartite matching problem. So you can write this, of course, as an LP with a corresponding TU matrix. That's the vertex edge incidence matrix or adjacency matrix. And so its corresponding problem, the dual problem, is the minimum vertex cover problem in a bipartite graph. Let's first try to interpret what interdiction means in terms of these two problems. So in the primal problem, interdiction means that you remove some of the edges. So let's assume that you have the unit cost case. So you can remove B edges, which is the same as setting B of those X variables to 0. So you force B of those variables to be 0, and then you optimize the remaining LP, and you want to set variables to 0 in such a way that the remaining LP has value as low as possible. In the vertex cover problem, of course, the two objectives are aligned. Right? You want to minimize the minimization problem now. So it's just a pure minimization problem. Since in the primal, it's about essentially removing variables, so setting variables to 0, which in this context is really just removing variables. That's the same as in the dual, just ignoring constraints. You can kind of remove constraints. So you can think of interdiction as a problem. If you think of it in a dual way about interdiction, it's the same as you're allowed to remove B constraints from your system, and you want to improve the objective as much as possible. So that's the same thing. It's just another way to look at interdiction problems. So those problems are actually typically NP-hard. Also even this problem here, similar simple problem, is NP-hard. Of course, it's strongly NP-hard. There are no large numbers involved. So it's also it's kind of interesting. One thing also I would like to let's first move on. Let's give a first general idea. So far I just gave interpretation of primal and how things can be interpreted in a primal and dual. But now let's if you actually want to solve such a problem, you probably want to have some kind of mathematical program that describes the interdiction problem. And so this is kind of there's no one-fits-all approach. So this is somewhat specific. So I do exploit the property of the maximum cardinality bipartite matching problem, which is that it's down closed, it's down monotone. So any subset of a feasible solution is feasible. In other words, any subset of a matching is a matching. So what you can do is, if you want to capture that you remove a variable in the primal, it's actually the same as setting its objective coefficient from 1 to 0. So at the beginning, you have an all ones vector in the objective, right? It's a maximum cardinality matching problem. If you set one of those, so R sets like certain of those coefficients to 0, setting a certain coefficient to 0 really just means it's the same as removing the corresponding edge, because there's no point to include that edge in any solution. For any solution that contains the edge, you can as well drop it now, and you have another solution of the same value. So it's really the same as if you just remove the edge. But this uses down monotonicity. Right? So why do you like to formulate it that way? Because now if you dualize it, because so see in red is the interdiction player, right? Black is the nominal, the player, the operator that solves the nominal problem. So because the interdiction player is in the objective, if you dualize, you actually get a linear program. Okay, you still have integer, you still have integrality constraints, so it's not an LP, but you get an integer linear program, or a mixed integer linear program to be precise. It's shown here. And now let's reinterpret things again. So it's still a vertex cover problem, but it's kind of a vertex cover problem where, now so this R on the right-hand side here, so I shouldn't use red, let's use blue here. This R here, essentially if you put one of the components to 1 in R, it's as if you deleted that constraint, because once you have a 0 there, so A transpose Y is larger or equal 0, so that constraint is trivially fulfilled, you just remove the constraint. So this really just captures the fact that you have essentially a vertex cover problem where you can kind of buy yourself out of covering some of the edges by paying with the interdiction cost. One thing that I find kind of interesting is if you look at the dual problem, it's almost a TU problem. Actually, so now keep in mind that the decision variables are Y and R. However, apart from that constraint here, from the budget constraint, the whole remaining system is a TU system, because it's just the matrix A transpose, and you've an identity matrix there for R. So essentially, so a lot of those problems, and also it's also true actually for network flow interdiction, such problems can be captured by a problem where you want to optimize over a TU polytope with just a single additional constraint. That's kind of an interesting problem class in itself. But it's typically, it turns out there are very hard problems in there in that class. So one other thing is that the dual can often be interpreted as a so-called bijobjective problem, or more precisely a budgeted problem. I will come back to that in a second. So here, let me give you first intuition already here, what I mean with that. So as I said, it's here with a vertex cover problem. So essentially, for every edge, you can decide either to cover it with one of the two vertices, and you have to pay for it in the objective by 1 unit because it shows the vertex. Or you can decide to kind of cover it by just removing the edge. So it's like two resources. One is the objective, and one is the interdiction budget. And with both of them, you can use both of them to cover edges. It's kind of a two objective problem. But let me be more precise about that. And it's kind of easy to see, or very nice to see in terms of if you look at the Maxim SD Flow problem. So let's look at the Maxim SD Flow problem. I want to show you how you can reduce the problem to a bi-objective problem. So that result is by Phillips of 93. So it's a pretty old result, but a very, very nice one. I'll give the proper reference later in a table. We have a lot of references. So again, let's just make sure we're on the same page. So I talk about Maxim SD flows. So you see here a graph. And so it's on planar graphs. So I want to simplify things a little bit. Let's talk about ST planar graphs. So the graphs that you can draw in a planar way, such that S and T are on the same face. And I will always draw those graphs such that they're on the outer face. So you see a max flow problem here. So every arc has two numbers. The first number is the capacity. The second number is the interdiction cost. And just to recap things, so here on the right, I drew the kind of for every possible, the different budgets that are possible. I indicated what is the best, after the best interdiction with that budget, what's the remaining flow. So let's just look at an example maybe. So if I look at, let's say this budget 5 here. So this point here means with budget 5, you can push the flow down to 4. So initial flow is 10. And so let me see how this is done. Yeah, exactly. You can remove these two edges, these two arcs. And this creates a cut, this cut here, which is value 4, 3 plus 1. Right? And that arc doesn't count, it goes the wrong way. So if you remove the two green arcs, you need budget 5 to remove them, and then you have created an SD cut of value 4. So that corresponds to that grid point here on the right-hand side. Okay, so far so good. So that's the problem. So of course we're given a fixed budget, and we want to kind of find the best interdiction strategy for that budget. But here I kind of give already somewhat too objective view on it. So here, of course, if the dualizing is kind of easy, the dual problem is minimum SD cut problem, and there's an easy way to describe this problem in terms of a planar dual. So in blue, you see the planar dual of that SD planar graph. So it's a bit of a modified one where you have like two vertices on the outer face, like a dual source and a dual sink. And it's not too hard to see that if you want to find the minimum SD cut, so they will correspond to a path from the dual source to the dual sink. So paths from dual source to dual sink correspond to SD cuts. Of course, there's some SD cuts that are not paths from a dual source to dual sink. You have like different parts of the graph that are not even connected in your cut. But if you talk about minimum SD cuts, they can be captured by paths in this dual graph. So think so let's look at this dual graph. So again, I will want to keep things on a somewhat high level. And so what I do is, so initially you had on the primal arc capacity and the interdiction cost. I will just copy those numbers on the corresponding dual arc. So the corresponding dual arc are kind of the solid blue arcs. I complemented this graph with backwards arcs, which have like 0 interdiction cost and 0 capacity. So the dashed arcs. So let's just look at the dual graph here. So this is really just, the numbers you see here are just the same. We had on the original primal arcs, so nothing changed. Let's first talk about minimum SD cuts. So if you want to just find forget about interdiction. If you want to find the minimum SD cut, that would really just be the problem of finding a shortest path from the dual source to the dual sink, and shortest with respect to the first numbers. So the first numbers are the capacities, right? So of course the minimum SD cut problem has nothing to do with interdiction costs so far. Now if you think about interdiction, so essentially you want to choose an SD cut, but for every edge in that cut you have a choice. Either the edge you will either interdict it, then it will not contribute to the value of your cut, but it will contribute to your interdiction costs, your budget. Or you will not interdict it, in which case it doesn't cost you anything in terms of interdiction costs, but it will, of course, incur a cost on the objective function. So you can capture this by simply replacing every arc by two parallel arcs, like one One is has the same capacity and zero interdiction cost, and the other one has zero capacity, the same interdiction cost. So one, of course, means you just remove the arc. So the arc 03 means you pay 3 units in interdiction cost, but therefore the arc is for free in your cut. Right? So the first objective, the 0, means that's what you pay for in terms of cut value. And the 1, 0 point is the 1, 0 arc is simply an arc where you don't remove the arc, and then you have to pay its original capacity, which was 1. So the interdiction problem now, the SD flow interdiction problem, or the problem of minimizing the minimum SD cut by removing arcs from a graph, is really just the same as finding a shortest path from the dual source to the dual sink. So shortest in terms of the first objective, so in terms of the first numbers here. But you're not allowed, so you will kind of also acquire like costs on the path, and the total cost of your path should not be higher than your budget. That's really just the same problem. And that's a well-known problem. That's the restricted shortest path problem, or budget shortest path problem that was solved by Warburton and Hassinger. Very nice papers on that one. So that's solvable in pseudopolynomial time. And you can transform this into an FP for this problem, actually. But it gives you a little bit I hope it gives you the idea how those things are connected. Interdiction problems are very often, you can really just formulate them in terms of a bi-objective or so-called budget optimization problem. And that's not just unique to this flow problem. The same can be done for the connectivity interdiction I showed you at the beginning, also for other problems, actually. That's kind of an approach that can work out. You have to think a little bit, if you think about connectivity interdiction at the beginning, for example, you have to think a bit how you would, you can actually transform it into a multi-objective global min cut problem. But it's not maybe as obvious as here, but still it's possible to do. So a little bit of work, one can do that. And that's the reason why it's, but actually the problem I showed you at the beginning is polynomial time solvable, because the bi-objective global min cut problem, or the budget global min cut problem, can be solved in pseudopolynomial time. And I showed you a problem with unit interdiction costs, so that's why it's polynomial time solvable. Good. So now comes the big table. So it's by no means, this is by no means exhaustive, this table. So let me first give you that disclaimer. So I just showed you a bunch of typical interdiction problems for typical combinatorial optimization problems that are polynomial time solvable. I mean, interdiction has been studied in a much, much broader context than that. So it's really just a very small excerpt of what has been done. And it turns out that there are pretty large gaps between the best approximation algorithms and hardness results. For shortest path, so everything is actually NP-hard, or at least weakly NP-hard. For shortest path, there's no approximation is known. The apex hardness is it's the best hardness we know so far about that. For the maximum flow problem, no approximation algorithm, no normal, pure approximation algorithm is known. Even though there is a so-called pseudo approximation, that is an algorithm that is allowed to violate a bit the budget. So it's not strongly NP-hard, just not strongly NP-hard. Yeah. So I kind of just want to highlight it. It's not strongly NP-hard. Yeah. And so maximum flow, no approximation algorithm is known so far. So previously the best hardness is always a strong NP hardness, and it's actually my poster with some very recent results there that show give another reason why this could be it could be difficult to find good approximation algorithms for maximum flow interdiction. The reason is if you can show that if you can find an alpha of n approximation for maximum flow interdiction, then you would get an alpha n square approximation for a densest case subgraph problem. So it's essentially a constant factor for maximum flow interdiction would imply a constant factor for densest case subgraph problem. So this may explain that column here a little bit for maximum flows. So in planar graphs, there's an FP-tas, which essentially follows what I just explained beforehand. So I talked about SD planar graphs, but the same idea works in planar graphs, actually. And it's too early to clap, Andras, but thanks. So for minimum spanning trees, so previously best algorithm was a log n approximation. And so as I told you, I want to talk a little bit about a very recent result of mine, a constant factor approximation in the second part of this talk. And then for matchings, there's a recent result by Anupam and Mike Dinitz, a constant factor approximation. It's actually based on results by Jochen and co-authors. And so there also is still a large gap because it's only strongly NP hardness is known. And connectivity, there's a p-tas. And so there's also more it's very nice to see that now recently more work has been, more work that is done on that in that field. Also, for example, for this pseudo approximation for maximum flows, there's also recent results by Tom, Britta, and Giampaolo that give algorithms to do this even quicker. So it's the same approximation guarantee, but it's quicker. There's kind of a lot of interesting work that is done currently. Oh, please.
What do you mean by connectivity?
So the connectivity thing, that was the problem I showed at the beginning, where you want to decrease the connectivity as much as possible. Yeah. So the same problem, interdiction has been also considered under various other aspects, like exact exponential time algorithms or fixed parameter tractability. So let me not go into that. It's too much to talk about. Let's move over to now to MST interdiction. So I don't have time to give all the details, but I will give you kind of at least a general idea how this problem can be approached, and also a little bit. I would like to put it a bit into context first. So again, let's just start with once more with the interdiction problem. So now the nominal problem is a minimum spanning tree problem. So so watch out, it's a minimization problem now, not a maximization problem. It doesn't change that much, but it's kind of important not to get confused. So again, you have a graph where every edge has a weight, it's the green number, and the interdiction cost, the red number. You're given a budget. You want to remove edges of total cost and most of the budget, such that in the remaining graph, in the graph you obtain after removing those edges, the value of an MST is as large as possible, right? You want to hurt the MST. So same setting as beforehand. That's just a formal description of it that just follows the same description as I showed when I formalized the interdiction problem. So there's nothing new here. There's one assumption I will make. There's a bunch of assumptions, but I'll start with one. One is I will assume that the budget is not large enough to disconnect the graph. So of course, if you can, first it's easy to check whether you can disconnect the graph. Just compute a min cost global cut and see whether it's below budget, and then you can disconnect the graph if this is possible. And so this is kind of easy instances when you can disconnect the graph. So I'll assume you're not in that regime, so the budget is not large enough to disconnect the graph. So before I want to talk about how you can try to attack that problem, let's first connect it a little bit to maybe better known problems. So let's first start with the maximum component problem, which is very related to the K-cut problem. So the problem is simple to describe. So you're given an undirected graph and the number q, and you can remove q edges, and you want to break the graph into as many connected components as possible. So again, the K-cut problem would ask you to create K-connected components by removing as few edges as possible. So it's kind of like the reverse thing. I tell you how many edges you can remove, and you want to maximize the number of components. But of course, it already shows, obviously, NP hardness, because the K-cut problem is NP hard. And if you can solve that, you can solve the K-cut problem. So that problem is really just a very special case of minimum spanning tree interdiction. And so let's assume this is your instance, and you're given some number q of edges you can remove. So what you can do is you can let's just add a spanning tree to it, so it doesn't have to use the original edges. I just added a star, which is kind of a simple spanning tree. And let's define the following weights and interdiction costs. So I want to define our interdiction problem, right, that captures the maximum components problem. So I want that the spanning tree I just added is not interdictable. So I'll make sure that its interdiction cost is larger than the budget. It's b plus 1. So the budget is the same as q. So b is equal to q. The weights are as follows. So the black edges are, so first the black edges have an interdiction cost of 1, so they can be removed. And the black edges have a weight of 0. The red edges have a weight of 1. So essentially the problem is you can only remove black edges if you want to compute the MST and whatever is left. So what would you do? You would first take all the free edges, which are the black ones, they're for free. And then you would complement with red edges, which you can always do because the red edges are spanning trees, so you can always complement with red edges, that's fine. And you would pay a unit for every red edge. And of course, the number of red edges you need is precisely the number of black connected components minus 1, right? It's the number of edges you need to connect the components. So it's the same problem up to an additive 1. So a closely related problem that I just want to mention because I want to refer to it later is the same problem like the maximum components problem. However, you could also have interdiction costs on the edges and an interdiction budget. And that is still captured by a minimum spanning tree interdiction in the obvious way. You would just copy those interdiction costs, so there's nothing changes. But so it's called the budget graph disconnection problem. I will briefly come back to that later. So once more, quick recap what was known about that problem. So a logarithmic approximation was known by Frederickson and Solis-Oba in a Soda paper of '96. And so for the case of the k most vital edges problem, that's just a unit cost case, where you can remove k edges. The same algorithm turns out to be a log k approximation. And that was the best one so far. And of course, one question was that there is no one approximation, which I want to talk about today. Another related problem that's sounds like a very simple problem. It is a simple problem, but it's still kind of interesting. So assume you want to remove a single edge, and you want to remove one edge to increase the weight of a minimum spanning tree as much as possible. That's obviously polynomial time solvable. I mean, just check all the edges, compute the MSTs, and take the best one, right? But it turns out you can actually do that in linear time with a randomized algorithm. So that's kind of interesting. So there are also results on that problem. Let me skip further to further related results in the interest of time. So as I said, I want to talk about the one approximation for MST interdiction. One thing that's kind of nice is that minimum spanning trees are often used as like a building block or a backbone of other approximation algorithms. For example, you can get, of course, a 2 approximation for TSP by doubling a spanning tree, a minimum spanning tree. And you can use such relations sometimes to get interdiction results for other problems, particularly for a TSP problem. So assume I'm a metric TSP problem, and let me phrase it in the following way. So I give you an undirected graph with length on the edges, and so the task is to find a closed walk that visits every vertex at least once. That's kind of a more natural way to describe the problem. I mean, often people look at the metric closure and they want to find a tour where every vertex is visited precisely once. But in terms of interdiction, it's kind of the more natural way to think about it. So you want to visit every vertex at least once. You have to choose a closed walk. Now assume that a certain number of edges can be removed from the graph, and you want to increase the length of a shortest TSP tour. So of course, since TSP is sandwiched, the value of a best TSP tour is sandwiched between the value of an MST and twice the value of an MST, same for TSP path. A constant factor approximation for MST interdiction immediately leads to a constant factor approximation for metric TSP interdiction. You just interdict the graph as if you wanted to find an MST. And that, of course, will also interdict it for TSP. So this implies a one approximation for interdicting metric TSP. Maybe some technical hurdles we have to overcome to find a one approximation for the MST interdiction problem is, first it's hard to find a good relaxation. So I'm actually, even for a k-cut problem, it's not so easy to find a good relaxation. I'm grateful to Chandra and Ravi, who told me recently about some results in that direction. So there are relaxations for the k-cut problem that are strong, but even that is not simple. And of course, MST interdiction is kind of a slightly different beast even. And another kind of difficulty is that MST interdiction can be interpreted as a multi-level budget graph disconnection problem. And I will come back to that in a second and be more specific about it in a few slides. So let me start with a few more assumptions that are kind of pretty simple assumptions, but they're important. So one is, I will assume that all weights are either 0 or a power of 2. So what I do is I just round them down to the next power of 2, or if they're 0, I'll leave them at 0. That, of course, changes the value of any spanning tree by most a factor of 2, so that if I'm looking for constant factor approximations, that's OK. I can do that. And we'll maybe lose a factor of 2 by doing that. So now the edges can be partitioned into the ones of weight 0. This is the E-1 set. And the ones of weight 2 to the I, which is the EI set. And the largest I denote by, so EP are the heaviest edges, so the edges of weight 2 to the P. Now I have a few further assumptions on EP I would like to make. So first, I will assume that an optimal interdiction set actually will never interdict, so that's not even an assumption actually, it even follows from what I said so far. An optimal interdiction set will never interdict an edge in EP. So it will never interdict the heaviest edge. The reason is the following. So interdicting an edge of a certain weight, the only reason to interdict an edge of a certain weight is to get an edge of an even heavier weight into the MST. There is no edge heavier than 2 to the P, right? And I assumed you cannot disconnect the graph, so there's no reason to attack edges of weight 2 to the P. So that's good to know. So you could kind of even assume that actually you have a spanning tree of edges in the set EP. Maybe this simplifies a little bit the thinking. You can think of it that way, and you only remove stuff from lighter edges. It's kind of one way to think about the problem. Another thing is that, another assumption I'll make is that I will assume that there is an interdiction set that is such that you will get a heaviest edge. It's possible to get one of the heaviest edges in an MST after interdiction. So there's a way to interdict edges such that an MST has to use an EP edge, an edge of weight 2 to the p. And of course, if this is not the case, then I could just delete all the EP edges and have the same problem, so I can simplify the problem. And I can easily check that if I want to see whether it's possible to force an EP edge to be in a minimum spanning tree. I just look at the graph on all edges that are lighter than 2 to the p, so 2 to the p minus 1 and lighter, and try to find a min cost cut in that graph. If I can disconnect that graph, I can force an EP edge to be in. If I cannot disconnect that graph, I cannot force an EP edge to be in and can delete all the EP edges. That's also kind of interesting. So that is actually I need that assumption for my relaxation to have constant integrality gap. It's kind of interesting. So now I would like to slowly move towards the high-level approach. So I use a particular way to evaluate the value of a minimum spanning tree. So it's a well-known way. So it turns out if I give you a graph and I ask you to compute the value of an MST in that graph, I mean, it's really just about finding, about counting the number of connected components in your graph of all the edges of like prefix edges up to a certain weight for different thresholds of that weight. So let's just, I'll just do that here. So in blue, you see the connected components of the graph if you only look at zero edges. So zero edges are the very thin edges, right? So if you remove all the other edges, then blue denotes the connected components of whatever is left. Of course, there are like, so let's see, there are like 5 blue connected components. This implies you need at least 4 edges of weight 1 or higher, right? And so in green, you see the connected components of edges of weight 1 and 0. So we have 4 such connected components. This means you need at least 3 edges of weight 2 or higher, and so on. So what you can do is, so you can therefore describe the value of an MST simply by computing the number of connected components for any, so E smaller equal I, or edges of weight 2 to the I or smaller or lighter, and you just compute sigma of that. It's the number of connected components you have of that in this subgraph. So you compute the number of connected components minus 1 and times 2 to the I, and the sum over all the i's. So essentially, this is a way how you can compute the weight of an MST. It's just one way to do it. Good. To simplify notation a little bit, so I will denote for any subset of the edges U, so use a subset of the edges, the value of U is simply the value of an MST after you remove U from the graph. So what is my, again, can I rephrase my goal? My goal is I want to maximize the value of U for a subset of the edges that is within the budget. It's the same, that's the problem I want to solve. So value of U is the value of a minimum spanning tree after I remove the set U. So here I would like to make this link. So essentially, now you see that, so if you want to minimize value of U, you somehow want to minimize, sorry, I want to maximize the value of U. Sorry. So you want to maximize the number of connected components in each of those graphs, kind of, right? So assume you want to maximize just one of those terms. And it's just a budget graph disconnection problem. You just look at the graph on those edges and just want to create as many connected components as you can. That's a budget graph disconnection problem. So the minimum spanning tree interdiction problem is to some extent like a layered budget graph disconnection problems have like one such problem for every I. Of course, those are structured, those layers, right? They're connected to each other. And so you can interpret it that way. And actually, the algorithm of Frederickson and Solis-Oba can be essentially interpreted as attacking only so kind of finding the best budget graph disconnection problem among those and only attack that one. So essentially, it's essentially that algorithm that they do. So they do not exploit any interactions between those layers. Now, let's talk about, so I would like to finish by quickly giving some ideas about what kind of relaxation I use. Let's first look at, so for every subset of edges I can remove, I can draw a dot in this diagram that on the x-axis shows the cost of removing this set. On the y-axis, what is the value of an MST after you remove that set. So here, what I've shown actually, what I've drawn here is a Pareto front of for that problem, so potential Pareto front. And the optimal solution is, of course, the one among all points that are that cost less than b. You want to have the one that is highest up, right? That would correspond to the optimal solution. There's a notion of, so you see I've colored some of the points in green. There's a notion of so-called parametric front. That's if you take the convex hull of all those points and look at like the upper left part of that convex hull, sort of the points that are on that upper left convex hull. I kind of connected them to simplify, to highlight this a little bit. So first observation, so it turns out we can compute those green points efficiently. Let me show you why. That's not so hard to see. So first, the value function is actually a supermodular function. The reason is it's like a conic combination of the sigma function that counts the number of connected components, and for a given edge set, and sigma number of connected components for a given edge set. That is actually also a supermodular function. Reason for that is you can, for example, describe it. If you give you any graph, you want to give a subset of its edges, you want to compute the number of connected components. It's nothing else than the number of vertices minus the rank of the graphic matrix. Right? And the rank of the graphic matrix is submodular, so the function will be supermodular. So it turns out that function here is supermodular. So therefore, now what you can do is you can mix the two objectives, the cost and the value objective, by some multiplier lambda. You can look at, for some fixed lambda, you can look at lambda times c minus the value of u. The really just corresponds to minimizing some direction of that type, so some go the other way, right? So maybe this would be like the optimal solution to that direction. So you can essentially, for every lambda corresponds to kind of optimize a linear function over this Pareto front, and that way you can get the parametric front. Now, of course, it's have to be a bit specific how you get precisely those points, because potentially it could be an exponential number on that front, but that's not the case, because it turns out, so this is a parametric submodular function minimization problem. So it's a submodular function that's parametrized by lambda. And it turns out that those problems you can find, if you let vary lambda, you can find minimizers that capture, such as a minimizer for each possible lambda, and those minimizers form a chain, so the sets form a chain. This implies it's just a linear number of different minimizers you have to consider. And so this means it's just that parametric front only has a linear number of vertices on the front. And it's actually even nicer. It turns out that submodular function minimization algorithms, they can find the whole chain, a whole such chain, in the same time as minimizing a single submodular function. So it's kind of nice. So it's what I will use to get all the green points. And so now to finish, I will just tell you the high-level plan. So the main technical theorem is the following. It's a theorem that tells you if you give me any set of edges to remove. So let's just look at one of those sets. Let's say this corresponds to some edge set to remove. So not necessarily, so any set. Let's take one. Doesn't even have to be on the Pareto front, of course. That is above budget, so it's more expensive than the budget. Then you can find a set. So first let's think of it as follows. So I like to think of sets as having a certain efficiency. Efficiency means what is the impact they have, the value, with respect to what they did cost. So it's like the slope from the origin to that red point. So I think of that as the efficiency. And sets that are further up have a higher slope. They, to me, they have a higher efficiency because they get more bang for the buck, right? For having the same budget, you get more higher impact, or per budget, you have a higher impact. So the theorem essentially tells you whenever you have any point, any set that is above budget, then you can find an interdiction set that's feasible, that's below budget, and whose efficiency is almost the same up to a factor of 6. So so the same efficiency would be like this point here. You won't get that, but you will get one that is maybe a factor of 6 first, so something of value roughly down here. That's the main technical ingredient. Let me just show you how we can apply that then. So what I will do is I will compute the two parametric points, the two green points, that are just the last one before that is still budget feasible, and the first one that's budget infeasible. And then I will invoke that theorem with respect to the infeasible point with respect to U2. So you will get, so before I say that, so first observation, so this point up here, this intersection of the budget value and my convex hull, that's actually an upper bound on the problem, right? Because all points are below the convex hull, so that is a relaxation. So I will compare against that, actually. So what the algorithm does is I invoke the theorem with respect to U2. So it's just the same, essentially the same drawing as beforehand. So you get a point that is feasible, but has maybe only a sixth of the efficiency of U2. Okay, as I said, we're looking for constant factors, so that's okay. And then it will simply return the better of the point you got there, the set you got there, for U1. And actually, if you believe in that theorem, it's very easy to see, it's easy to compute that this algorithm is a 7 approximation. So it's kind of a simple calculation that has to be done here. Good. So let me skip the details how this is done. So it's kind of the technical part. And let's just summarize quickly. So so it's actually this leads to 7 approximations I said beforehand, but remember I had the assumption that weights are powers of 2, so I lose another factor of 2 because of that. That's why it's a 14 approximation. So I didn't really try to heavily optimize constants, so maybe one can improve that quite easily to something a bit better. I don't know, but it's nice to have already somewhat reasonable constant. And by what I mentioned at the beginning, this implies a 28 approximation of a metric TSP interdiction. So that's essentially all I wanted to say, so I hope I was able to give you kind of an idea of interdiction problems and some general insights of how it can be approached. And of course, I'm more than happy to answer any questions. Thank you.
It seems to me that a lot of this actually could be applied to any matrix where you can compute the minimum cost. So like not all, but
yeah.
Some of the arguments. So
that's a good point, yeah. So there is so I do exploit some properties. So for example, there's a result by Adrian Vetta and Cotter who show that if you look at a transversal matrix, then the problem is actually pretty hard. So there too, it's as hard as essentially solving a densest case subgraph problem. So so it does not extend to general matrices, but maybe there's some class of matrix that could still work out.
So the factors, the number 6 in that lemma, do you have any sense of how tight that is?
That's a good question.
Probably be better.
Yeah, I don't think it's tight actually. I'm pretty sure it's not tight, but it's tough for me to give a good guess what the right constant should be. I don't know. But I agree with you. It would be highly surprising if 6 is tight.
So initially you mentioned that you can think of like a game. Some people look at game interdiction problems as well.
Yeah. So we had kind of in some of the previous talks also by we said yesterday, like by Gruya and I mean there's also kind of game theoretic notions where we have like when players start playing simultaneously, then you can think of it as a game, right, where you have Nash equilibrium and they try to achieve a Nash equilibrium. So this is one kind of I mean there's more results on such things. Also I know that also Michel worked with a student on similar problems actually. So this is one type of game theoretic problems. Maybe there are more, but I'm not sure about that.
For these two problems, you mentioned the interdiction of flow in discrete name-wise and matrix interdiction, MST interdiction. What if you choose a flow or an MST before the interdictor to these edges? So this is a question Tom raised.
Yeah.
Anything beyond that for discrete name-wise?
So if we now talk about, so for flows, I don't know whether in a planar setting things get easier. I don't know. For spanning trees, you would have to agree first what it means. I mean, if you first choose the spanning tree and then the interdictor destroys stuff of the spanning tree, so what exactly would you evaluate then? I mean, in the flow setting was kind of, the solution to that was, or one way to interpret it as a way we've seen here is that you assume that the flow player has to choose a path decomposition as well with the flow. I mean, the main reason for that being that if the interdictor starts interdicting, then you know what is kind of the flow left, right? But in MST, you would need a similar notion first before we could even talk about what we optimize, I guess. Yeah.
So for the basic problem where I guess you have a budget on Q and you want to maximize the number of connected forms.
Yeah.
Right? That's kind of the goal of the K-cut.
Yeah, the maximum components problem.
So from your result, you'll get
I would guess so. But there you can get, actually it's easy to get constant factors for those problems. So there you can get like a 2 approximation, the same approach as the K-cut problem.
So there is a 2 approximation.
Yeah, exactly. So there, for those problems, there's very special cases, constant factors are known actually, yeah. But the funny thing is it's open whether there could potentially be a p-tas even. I mean, nothing outrules a p-tas so far, but the problem is kind of interesting.